Today, we're going to get into one of the most important stories in all of science. It's about a really simple puzzle. I'm talking light and heat that didn't just stump the world's best scientists. It completely shattered their understanding of the universe. And in doing so, it gave birth to a whole new reality.
So, it all starts with a question you've probably seen the answer to, but maybe never actually asked. Why does a hot object, like an electric stovetop or a piece of metal in a forge, start to glow? And why does it go from red to orange to maybe even a blazing white hot?
Seems simple, right? But back in the late 1800s, this question was an absolute nightmare for the greatest minds alive. They threw every single scientific law they had at it, and every time, their theories just failed, spectacularly. It was that failure, that one little crack in the foundation of physics, that blew the doors open for the quantum revolution. So let's get right into it.
Okay, so the first step here is to understand what exactly these scientists were looking at. The mystery wasn't just that things glowed when they got hot, but how they glowed. The specifics were everything.
They started seeing a really clear pattern everywhere they looked, from something as simple as a candle flame to stars billions of miles away. And the pattern was this. The color of the light is directly tied to temperature. You can see this for yourself in the constellation Orion. The star Betelgeuse has this reddish glow, right? Well, it's actually cooler than the brilliant blue star Rigel. So the rule they figured out was, the hotter the object, the shorter and bluer its light is. This was the key clue.
Now, to study this in a lab, physicists needed a perfect test subject, something totally pure. So they came up with a theoretical idea called a blackbody. Imagine an object that's a perfect sponge for radiation. It absorbs everything that hits it. And because it doesn't reflect any light, any glow that comes from it is purely a result of its own heat.
Of course, a perfect blackbody doesn't actually exist. But scientists are, pretty clever. They figured out that you could build something really close. Just take a hollow box and poke a tiny little pinhole in it. Any light that goes into that hole gets trapped, bouncing around inside until it's totally absorbed. And then the heat radiates back out of that same tiny hole, acting just like a perfect blackbody. This simple little box gave them something they could finally measure.
And when they did measure it, the results were just beautiful. I mean, look at these graphs. For any temperature, the radiation hits a peak at a very specific color, and then it just elegantly trails off. And as things get hotter, that peak shifts up towards the shorter, bluer wavelengths, just like they saw with the stars. The data was perfect, clean, predictable. The only problem? No theory in the entire world of physics could explain the shape of these curves.
And this is where the story gets really dramatic. See, scientists were confident. They had the laws of thermodynamics, of electromagnetism. These were the pillars of 19th century physics. They thought explaining these curves would be a piece of cake. Oh, were they wrong.
So their best shot came from a formula we now call the Rayleigh-Jeans law. It was built using all the common sense ideas of classical physics, that light is just a continuous wave, and that energy is smooth, like a fluid. It can be divided up into any amount, big or small. And at first, it looked pretty good. For the long wavelengths, the infrared and red light, the theory matched the real-world data perfectly. They thought they'd nailed it. But when they looked at the shorter wavelengths, like ultraviolet light, the theory didn't just break down. It went completely insane. While the real experiment showed energy peaking and then falling off, the classical theory predicted that the energy would just keep going up and up toward infinity.
I mean, this wasn't just a small rounding error. It was a complete failure of physics. The theory predicted that any hot object, your stove, a candle, you, should instantly blast out an infinite amount of energy as ultraviolet light, X-rays, and gamma rays. Our cozy fireplace should be a death ray. This failure was so total, so spectacularly wrong, it earned a very cool, very dramatic name, the Ultraviolet Catastrophe.
So physics was broken. According to the best theories they had, the universe as we know it shouldn't even exist. The whole field was in crisis. And it needed a hero, someone willing to try something that sounded absolutely crazy. That hero was a German physicist named Max Planck. In 1900, after trying everything else by the book and failing, he decided to do something completely radical. In what he later called an act of desperation, he decided to break the biggest rule of all. He asked a simple question: what if energy isn't smooth?
And this is the absolute core of the whole thing. The classical view was that energy worked like a smooth ramp. You could stop anywhere on that ramp. You could have any amount of energy. But Planck's wild idea was that energy is more like a staircase. You can stand on step 1
Or step 2, but you can't just float in between. Energy, he proposed, could only be absorbed or given off in specific chunky packets.
So this meant that the tiny little oscillators vibrating inside the walls of that black body couldn't just have any random amount of energy. No, they were stuck on specific energy levels like the rungs of a ladder. To jump up to a higher rung, they had to absorb one exact chunk of energy, and to fall back down, they had to spit one out. Planck called these little energy packets quanta, and he even came up with a beautifully simple formula for them, E equals hf. Here, f is the frequency of the light, and h is this brand new magic number for the universe, which we now call Planck's constant. The really critical part is what this formula implies. High-frequency light, like ultraviolet light, has to come in really big, high-energy packets.
And that lumpy view of energy was the key. It completely solved the ultraviolet catastrophe. Why? Because at those high frequencies, the energy steps on the ladder were just too big. The little oscillators inside the black body didn't have enough heat energy to make those huge jumps, so they just couldn't make much ultraviolet light. When Planck put this whole idea into a new formula, it didn't just get close, it matched the experimental curves perfectly across the entire spectrum. The catastrophe was over.
So the problem was solved, but in solving it, Planck had accidentally unleashed an idea that was way more revolutionary and way stranger than he could have ever guessed.
At first, nobody really believed it was real. Not even Planck. He thought he had just stumbled onto a clever math trick to make the equations work. The idea that energy itself was fundamentally chunky, that it was quantized, it just seemed ridiculous. It had to be a trick, right? Not the way reality actually worked. But then, just 5 years later, a young Albert Einstein took Planck's trick very seriously. He realized these energy packets could also perfectly explain another weird mystery called the photoelectric effect. And Einstein took it one step further. He proposed that it wasn't just the energy exchange that was chunky. Light itself was made of these little packets, which we now call photons. And just like that, Planck's idea went from being a math curiosity to a fundamental truth about our universe.
And the impact was, well, it was everything. Planck's act of desperation became the first stepping stone into the bizarre world of quantum mechanics, introducing wild ideas like wave-particle duality. And it's the foundation for almost all of our modern technology. Every laser, every transistor in every computer, every single smartphone, they only work because we understand this one fundamental principle: energy comes in packets.
So it all started with a simple glow from a hot piece of metal. But it ended up forcing us to accept that we live in a strange, grainy, quantized universe. And it leaves us with this incredible thought to chew on. If something as basic as energy is lumpy and not smooth, what other parts of our reality have a secret pixelated nature that we just haven't noticed yet?